Hello and welcome to our lesson on rivers. Today we're going to be looking at the processes, in particular erosion. So our three key takeaways are to describe the different processes of erosion on a river, to explain how and why they change along a river, and to link these processes to different locations along the river. So if you have a pen and paper, it will be brilliant to jot this down. Erosion, this is basically a process where the river wears down its bed, which is the bottom of the river, the banks, which are the sides of the river, and the sediment within the river. So this is what the river could be carrying, okay? And by wearing it down, it basically means breaking it apart into smaller pieces, and that's the process of erosion. So in order to do this, the river needs energy. In theory, the more energy a river has, the more erosion can take place. The less energy it has, the less erosion can take place. So there are two questions that while you're jotting that down, we can think about, which are basically what do you think happens to the river's energy as we go downstream? So from the upper course to the lower course, and why do you think that will be? And you can use the information to help you on the screen below. So on the left, we've got a river in the upper course. On the right, we've got a river in the lower course. So think about how the characteristics change. We've got a diagram that can help you, or an image below the table that can help you explain why that is happening. And then you can also use this little extract from the Bradshaw model, that little triangular shaped piece in the middle. This basically shows how discharge and velocity change from upstream to downstream along a river. So it shows discharge and velocity. Velocity is the speed of the water, and discharge is the volume of the water and the speed at a certain point. So as the triangle gets bigger, it will show that that value becomes higher. So the first bit will be to think about that little question. The second question we want to be aware of is what might the difference between vertical and lateral erosion be? Because this also changes along the river, and it's another form of erosion that we just need to be aware of. So hopefully you've had a little bit of time just to think about what happens to the river's energy as we go downstream. So basically, if we look at the diagram, we can see that up here the river is pretty narrow. As we go further down, we can see that zoomed out, but it's much, much wider. Okay, we can make the assumption where we can see white water, that the water is going to be a little bit shallow. We can also see that the water is dropping, it's cutting downwards here as well. Okay, but we can see a small stream, and then at the bottom we can't see any white water, but we can see that the river is very flat. Okay, so we'll just put these annotations. So there's a lot of flat land around it. Not much is changing. We can't see the bottom, so we can make the assumption that it's relatively deep. So what we'll do, we'll work with this information. So in the upper course, the river is shallow and narrow. Okay, so therefore it has a small discharge. Okay, or it has a smaller volume, and therefore ultimately its discharge will be smaller. We can see that that agrees with what we can see in the Bradshaw model. Okay, it matches what we can see there. So there's a smaller discharge, it's got a smaller volume in the upper course. Obviously we can see that that is opposite in the lower course. So lower course, the river is wider and deeper. We can't see any white water. We can assume that it will be deeper. And therefore, it has a larger volume. This links into our discharge. Okay, so we can tell these characteristics are already happening. Okay, now if we were to stand in either of those rivers, the upper course river wouldn't really be able to sweep us off our feet. It doesn't really have enough power to do that. Okay, so that smaller discharge shows the upper course. So this river has less power. Therefore, it's going to have less ability to erode, so less erosion will take place. Now, in our lower course, we are looking at the complete opposite. So here, the river is more powerful, so therefore more erosion will take place. Okay, so if there's more erosion taking place, then more material will be broken apart. We might see that the bed and banks of the river might be deeper and wider, which is what we evidence here. Okay, so we can make the assumption that our river is gaining energy as it goes along its course. Okay, now we need to identify why that is happening, and that comes down to two different elements. So here we can see on this diagram right at the bottom, we can see one stream, which is known as a tributary, coming from this direction, one coming from this direction. Now, when they both meet, which is at a confluence, their water volume doubles. Okay, so we've got two what we call tributaries. So two tributaries meet. And this is at a confluence. So at the confluence, which is the point where they both connect, okay, at the confluence, the volume of water increases, okay? So because the volume of water increases at the confluence, there's more energy, and I'll just put this box over here. Oops, let's get rid of this one. And we'll put this over here. So where these two streams are meeting, that water is increased, the volume of water, and therefore the river has more power. So you can kind of see from that picture that river after the point they connect at that confluence, the river actually becomes wider. Okay, we can see that width has already increased, and we can identify that from this narrow one, this narrow one. We've already seen that that is much wider. Okay, so the volume's increasing, therefore the power the river has also increases. And these connection points happen quite a lot along the river's journey. So the energy is increasing. So the next thing brings us over to what we mean by vertical and lateral erosion. So in the upper course, the river's aim is to cut downwards, trying to get down to sea level. And we can visually see the water is cutting downwards here, especially at this point where we can see a waterfall. Okay, a little mini one, but the water is falling. So we can see the river is vertically cutting downwards. So that's quite important. So I'll just highlight that over here. So this is vertical erosion taking place. Now, when the river is near to its sea level, it doesn't need to cut down any further. So therefore, it's going to be eroding laterally or sideways. Okay, so this is where we get certain other features like meanders, where there is lateral erosion taking place. The river doesn't need to go below sea level. Its aim is to get to sea level. Once it's near to that point, the vertical energy is transferred to more lateral energy, which we will visually see with a flatter river in the lower course and a more vertical river trying to cut downwards in the upper course. Okay, so at this point we know that the river's energy increases, and it starts with vertical erosion, not much power, and it increases as rivers meet together to increase the river's energy and power. And as it gets nearer to sea level, it will transfer to lateral erosion. So what we'll do, we'll clear these and we'll move on. Okay, so these are the four different types of erosion that you need to be aware of. You can have a little look at the definitions here, and you can think about which ones might match. You use a diagram in the middle. So hydraulic action is linked towards these cracks in the banks of the river. Solution you can't actually see. It will be invisible to the eye. Abrasion, we can see sediment or material at the bed of the river. And we can see attrition. It looks like there's floating sediment there, which looks like it's getting a little bit smaller. Okay. So first of all, we want to match these definitions. These are key terms that we need to know. So what we'll do, let's start with, we will go from a material being dissolved, okay? So you might look at this in chemistry, for example. When you dissolve sugar in water, you're putting it into a solution, okay? So solution is material being dissolved. Once it's dissolved, it's invisible. You can't see it anymore. Okay. Then we can look at the next definition. So sediment in water, is dragged against the bed and banks of the river. So it's got to be in contact with the bed and banks of the river. It looks like the only one that can do that from the diagram is abrasion. Okay. So abrasion, we can see all those boulders and sediment at the bed of the river that's being dragged along, a little bit like a sandpaper effect. Then we've got the sheer power of the water wears down the bed and banks of the river. Well, we're not floating in the middle anymore. We're right on the edge, bed and banks of the river. So this is hydraulic action. So hydraulics, just picture that word hydraulic and that'll give you the indication that we're talking about power, just like in machinery when they use hydraulics to lift weights. Hydraulic action is the power of the water. Okay, so it needs a lot of energy for it to do that. And therefore, process of elimination, where we can double check, sediment is knocked together, becoming smaller. In theory, it could happen on the bed of the river, but process of elimination, it will be attrition. So when sediment is being carried in the water, it can be ground together. So it doesn't have to be floating. It can be at the bottom of the river as well, at the bed of the river. But that's where they're grinding past each other. So it's not the bed and banks of the river that are getting eroded. It's the sediment within the river that gets eroded as the water knocks particles together. Okay. So what we'll do, we'll clear this and we'll see if we can identify some of the processes, what might be happening at different parts of the river. Okay. This diagram will come up so we can reuse it as we go along. So which form of erosion might we find in each of the following images, and why? We got two images, one left, one right. Okay. So obviously you can use this diagram to help you remind you what some of these words were. Now in theory, we could say that solution could happen in either, because solution will be dissolved material, so we won't see that anyway. Okay, so that could potentially be dissolved material in here. It could be dissolved material in here. The water looks really clear. Okay, so that's what we could be finding there. Okay, obviously if we look at power of the water, whoops, we'll just amend that to a box. So hydraulic action, the power of the water. So we're looking for any intensity that we can see there. So the power of the water, we can see at this point, you can see a huge amount of power as it's coming down. It might be a flash flood or something like that. So there is power there. So potentially hydraulic action could be taking place. We can also see power here as the water is falling down. It's got a lot of gravitational potential energy, or gravitational energy, movement energy anyway, through kinetic means. There's basically a lot of power being created at this waterfall. Okay, so we can probably assume that hydraulic action will be taking place. If we look at our next one, let's look at attrition. Whoops, same again, I'll change that into a box. So attrition is sediment that's being carried. So this one, well, can we see any sediment being carried in here? Well, not easily, not visually. There probably is, but we can't visually see it. Whereas if we hop over here, same again, I'll change that to an arrow. If we look over to the far side, we can see that the water is really brown. Okay, so from our transportation lesson that we've done, we know that there's a lot of material in suspension there, so it's being held. So therefore, we can possibly assume that attrition could be taking place with the power of that water. It could be knocking together particles of sediment. Okay, and then our final one. So we will choose orange for this. We'll look at abrasion. So with abrasion, we're looking at material being dragged basically along the bed and banks of the river. Now, if we look, so I'll just draw this over a box. So abrasion, visually, we can't see it on the right. We can maybe assume it's happening, but we can't really clearly visualize that. However, we can see that there is sediment on the bed and banks of the river. We can see the sediment. We can see the river's got a lot of energy as well. So we can assume that that river will be moving that sediment, scraping it against the river channel like sandpaper. Okay. So obviously to know all of them, to put them all together, chances are a lot of them would be happening. But in this case, we can probably identify the ones that we can see on the picture quite clearly from that. If we are looking at where this might be happening in terms of a river, vertical or lateral erosion, for us, we'll probably have to argue that here we can see water is falling downwards, so therefore we know that we're not at sea level, so vertical erosion must be taking place. Now we can also argue that with our image on the right, because we can see a step in the foreground. We also can see that there's steep terrain in the background, so therefore we can make the assumption that we might be still in the upper course where the river needs to erode downwards. Okay, so we can put together these kind of assumptions. So what we'll do, we'll pick one more image out and then we'll do a summary. So I'll clear all of these and we'll look at the final one. So this time we'll move away from that diagram using those key terms, and we'll use the Bradshaw model, this little extract, to justify which process would be happening at each of our original sites and why. Okay, so in theory, we're looking at the Bradshaw model shows low discharge in the upper course, high discharge and velocity in the lower course. So therefore, we can assume that the river is going to have less energy here to erode, and therefore, if we go to the image on the right, the lower course, we can say it's got more energy to erode. So this goes back to the principles of how the river changes as we go downstream. So if we continue with that idea, well, we can see definitely that vertical erosion is taking place. So that's one erosion form that we can identify. We can also say that lateral erosion is taking place. So we'll add those two forms in. So we're in the upper course, so it must be vertical erosion taking place. We are now in the lower course on the image on the right, so it must be lateral, the sidewards erosion taking place. Okay, and that's why those two landforms look a little bit different. In terms of the Bradshaw model, we can assume, or we can make the assumption that in this river we've got high discharge, high velocity, so we're looking at a lot of power. So therefore, where there is a lot of power, we can make the assumption that there would be more hydraulic action taking place, because that's the power of the water. So that's the assumption that we can hold at this point. In theory, the water also looks relatively clear. So potentially we could also put through the point Well, we'll never know it because we can't see it, but there could be material in solution as well. Okay, there could be material in solution which is dissolved as the river moves. Now, with this similar point, the water in the upper course is also clear. Okay, we know that there's much less power here. Okay, so there's not going to really be much hydraulic action, maybe a little bit in that waterfall. Okay, but potentially the only thing that we can really identify, and this is all possible, would be solution. Okay, at the moment the river doesn't have enough energy to really make significant erosion. There might be a little bit of hydraulic action where the water is falling, but what will play the largest role in eroding this channel will be a storm event. Okay, so I'll just put this in a different color, so I'll put it in blue. So in the upper course, significant storm events can provide enough energy for the river to erode. Okay, so in these events, that's when the river will mainly catch up most of its erosion. That's when all of those forms of erosion will be more significant, when it's got more power in those storm events. Okay, so what we'll do a quick summary. So you can just get a summary, double check everything that we've done. So in terms of our 3 key takeaways, we have identified the 4 key types of erosion. So hydraulic action being the power of the water. Abrasion is the sediment wearing away the bed and banks of the river. Attrition is the sediment being knocked together. And solution is the dissolved material. So water dissolving material. So in terms of where they will happen and why they'll happen in the river, vertical erosion always happens in the upper course as the river is trying to cut down to sea level. Lateral erosion is where the river is in its lower course, middle to lower, where it transfers its vertical energy to lateral energy. As it's nearer sea level, it doesn't need to cut down as significantly anymore. Okay, so lateral erosion is in the lower course of the river, nearer sea level, and erosion increases as volume and speed of water increases. Okay, so that's what we mean by discharge. So that happens when 2 tributaries, 2 small streams connect together, add their water supplies, and therefore the volume of water now being moved along the river increases, and therefore so does the power of the river as well. And therefore, in terms of our locations along the river, upper course, we tend to see more vertical erosion. It has lower energy, so lower rates of erosion. Only exception would be in storm events. And then the lower course, you're going to find more lateral erosion, tends to be higher energy, and more erosion types can be found in the lower course at a more consistent duration. Okay, so we'll leave it up there. Thank you very much for watching and have a good day.